ऐसा yawning करोगे तो मैं पढ़ाऊंगा कैसे?
Sir, I was already asleep here.
Yeah, I saw that. That's why I said. When did the school end today?
Same time, but after 4 days of holidays.
Yay!
Aditi!
Thank you. Okay, maybe अभी हो गया.
Suli. आई थी ना भाई.
Okay. Somebody tell me where did we stop in the last class?
Maybe questions.
Of?
NCR. We did numericals of NCR.
We are still doing or we completed?
Completed. We need to start with sounds this time. We had discussed this last time.
Okay. Sound we had started?
No.
All right, let's get started. So this is going to be a last lecture. So I think we should be able to finish it in few lectures, 3 to 4.
Thank you.
Excuse me. Sound started with that. Okay. So any idea what is sound?
Volume?
I did not ask how it is produced. What is sound?
We just listen.
It's a type of energy. Okay. So precise thing is sound is a type of energy which does what? That produces sensation of hearing in our brains. Okay.
This will be happening 15, right? So 12.
That produces like what? Music and no. That's range. We'll come to it. That produces sensation of. See, you mean something, but it has to be defined properly. So I'll explain what's the difference. Okay. That produces sensation of hearing in our brains. Where do we hear sound? Brain or ear?
Yeah. Brain also.
Actually, when the vibrations pass,
So what happens is ear now vibrates.
Yes.
That sends electrical signal to brain. And then brain recognizes that as a sound. Everything is recognized by brain. Eyes, ear, these are just tools. Okay? They feed data to brain. Okay? So this is what is sound. Next is how sound is produced. So let's discuss what is production of sound. So sound is produced by any vibrating object. Okay, sound is produced by any vibrating object. Is it always true? Sound is produced by any vibrating object?
No.
Not true? But you just heard sound.
yes, sir.
You don't hear sound.
Can you hear this?
Sir, but there are those sounds.
There are species who can hear this sound also, but not we. Okay? So this is vibrating, but is it producing sound? No. It's not producing sound to us. But it can be heard by bat. Bat.
The dogs.
Not dolphin.
Dogs are high frequency.
Elephants, whales, they can hear it.
I understand the concept that we cannot hear sounds with that low frequency. Then why can't we hear sounds after a certain like
Yeah,
beyond
so
that
that's the limit of our sensation. Every vibrating object can vibrate with whatever limit it is capable of. The lowest and the maximum limit is set for a vibrating object. So our ear can detect sound between 20 and 20,000 hertz.
Yeah.
not before, not after. Okay, so that is the audible
What
range.
happens to the sound when it is like 30,000 hertz or something?
So brain does not process it.
So we go deaf.
Simple. No, yeah, you go deaf for all the frequencies above 20,000 hertz. Okay, so so sound produced by the vibrating. So humans can hear sounds of objects vibrating with frequencies between 20 hertz to 20,000 hertz. Okay, you understand what is frequency? Have you defined it? Have you defined frequency
No.
in lower class? Have you studied in it? Vibration frequency, is the term frequency introduced to you? Not yet. So if not, we will learn what is frequency. Okay.
So we are done it, but we don't.
I'll tell you what is frequency. I'll tell you. Hertz or per second. See what is a cycle? We did what is one cycle, one oscillation in the last chapter. Oscillating pendulum, right? So therefore, the oscillation starts from here. 1, 2, 3, 4. This is one oscillation. Mean position, one extreme, again mean position, other extreme, again mean position. Is one oscillation. It is in 4 steps. Okay? 1, 2, 3, 4. This is one oscillation. So what is frequency? Number of oscillations in 1 second in unit time. Number of oscillations for unit time. Like in 1 second, how many vibrations? Let's say 10. It is producing maybe 10, not even 10. 1 or 2. What is 1 second? This duration between 2 ticks. Okay? That's 1 second.
We can calculate it by simply saying 1001.
So
That's
just
1 second.
watch here. It's hardly one and a half frequency. Got it? So it's like that. So number of oscillations in 1 second is frequency. Okay, so this frequency range is called audible range for humans. Audible range. For humans. Is it clear? Now next, propagation of sound. Now this is the most important topic in this chapter, so I would request you all to pay full attention here. This is the most critical topic.
My bag fell down.
Your bag fell down?
Yes.
On by me.
Sorry.
Okay. So propagation of sound. What is the meaning of propagation? How sound travels. Propagation means how it travels. I am speaking here. So the source of sound is here, fixed. But she can also listen, see everybody. Okay? If anybody is hanging up there behind, everybody will be able to listen to me. So it's propagating in all directions. Right? That's why everybody is able to listen to it. How are you able to listen to it? What's the process? If there was no air, in vacuum, will you be able to hear my? No. You may see only the movement. Optical information will be there, but there will be no hearing. Okay? So you basically require a medium for sound to propagate. What's the medium in this case? Air. So air is one medium. It can also travel in solid. Let's say if you keep your ear on the tabletop and knock, you will still hear. So sound can travel through solid as well as liquid. So it can travel through all 3 mediums. Understood? So for propagation, sound, it requires a medium for propagation. So let us understand it with the help of a demonstration. Let us say you have a sound producing object called tuning fork. Have you heard of
What is
it?
this exactly? I had it in my textbook last year.
Yeah. So what is tuning fork? Let us say it is a steel rod bent into U shape. U shape. Okay. It's a steel rod bent into U shape and a stem of the same material is fixed.
So when we hit it, it produces frequency.
Yes. So let's say even if it is not a tuning fork, if it is a rod, if you hit it, it will vibrate and produce sound, isn't it? So this is a specially made object as a turn kar diya, so that it gets U shape and a stem is fixed here somewhere, so that you can hold it. Welded, stem is welded in. Okay. So now, like you said, if it is hit on a rubber pad, then it will start vibrating like this. This is slow motion, it will vibrate very fast. And you can hear a humming sound.
Yes, sir, it comes.
So in lab, you are supposed to basically do this experiment. I don't know whether your school has
Sir,
done
we
this.
had it last year, last
You've done it last time. Okay. So this is called tuning fork. So these two things are called its prongs.
Sorry?
Prongs. It has got these two prongs. And once it is hit on a rubber pad, it will start vibrating back and forth like this. So it will make, so how it is oscillating like this. Like this. It is making forward and backward movement, right? Let's say somebody is listening to the sound produced by tuning fork over here. Let's say this is the ear of the listener. So you have a listener here. Okay, this is the source of sound. Okay, so it has to be vibrating object. Now, between the listener and the source of sound, you have to have a medium. So medium is air, right? Now initially, imagine there is a uniform distribution of air molecule like this. Uniform.
True for like actual air molecules, because air molecules are always flowing.
So imagine there is no wind, okay, like in a closed environment. So if there is no sound, the air molecules will be uniformly distributed. Okay?
Like a partial vacuum.
No, there's nothing called like, yeah, you can say that maybe. There's no movement, what I mean to say. Okay, like this. So the molecules will be evenly distributed. That's what I mean to say. Okay. Alright. So you have even distribution. Now this is a difficult concept to catch, so pay full attention. Then we'll see a video animation also, so that it becomes clear. Okay, so now it is a uniform air molecules. But now this is the situation when it is not vibrating. When it vibrates, what will happen? These air molecules will be pushed forward. They will be pushed forward, right? So if this moves forward, so if this is disturbed due to this, when it is pushed forward, it will disturb the adjacent molecule, neighboring molecule, right? Then that will catch disturbance and it will disturb the neighboring molecule. So what is happening? The disturbance is transferred from molecule to molecule. Okay? Then finally, the molecule which is in contact with the eardrum will disturb the eardrum. It's like there is a queue of students, right? I push the last student or the student just ahead of me. He will disturb the ahead of, okay? And that disturbance will disturb the first student as well. So what has passed is disturbance. Is the last student gone to the first student? No. What has gone? Just the disturbance. Exactly that is what happens here. So what is the disturbance? Motion. What is motion? Kinetic energy. So basically what is passing through the disturbance? The energy. So sound energy here is converted into kinetic energy of the air molecule, and that energy is transferred from molecule to molecule. Finally the eardrum starts vibrating. You understand? and then those vibrations are caught by brain and perceived as sound energy. Clear? This is how. So how can we write? So sound propagation takes place through the medium what is medium here? Air. By way of transfer of disturbance from one particle to other particle of the medium. Okay? Through a series of compressions and rarefactions. High pressure and density. Compression and rarefaction. Low pressure and density. Okay. So initially, if you see, if I represent this in form of line, so these lines will be evenly spaced throughout. Straight, huh? So what are this straight line? Just the air molecules, evenly spaced. Now when the tuning fork is set into vibration, some of them will form closed region, some of these will spread out. Okay? So this kind of closed formation and spread out formation will take place. Okay? And now it will be spread out. So this is like rarefaction, right? More spread out. So these regions are called compressions. When this compression is flowing, the series of compression and rarefactions are formed. So when the molecules are packed into smaller region, that's when the pressure and density will increase. That is called compression. But when the tuning fork goes back, that time these molecules will start coming back. So molecules, if you see, the molecule is not moving. Molecule is also oscillating at its mean position. So each molecule is oscillating. The molecule is not traveling, it's not leaving its position forever, I mean to say, it's just oscillating. And while doing that, so it went and collided with this. So when it collided, it went ahead and now it is coming back. So rarefaction. So compression and rarefaction is a continuous process. And what is transferred ahead is energy from molecule to molecule. Is it clear? So during this also you must know, during sound propagation, duration of sound, the air molecules of the medium medium, oscillate at their main position. Main position means rest position, when there was no sound, that position. So forward and backward motion. Only the disturbance is passed from so this disturbance is called wave. What is it called? Wave. Only the disturbance is passed. So disturbance is nothing but energy. It is passed from particle to particle, air particle or air molecule. Particle can be molecule also. From air molecule to air molecule. Air molecule. Is it clear? Is it clear?
Yeah, the vibration. Sorry.
The propagation.
Yeah.
So the disturbance has got a specific name. What do we call it? Wave. Okay. So that's why sound is basically sound wave, sound energy. Wave means energy. Disturbance means energy. So all the different terms given to the energy only. So wave is also a mode of transportation of energy. How it is transferred? In the form of disturbance from particle to particle. Okay? And the particle is not leaving its position. It's just going forward, backward at its main position. Clear? So we will now represent it graphically. First you write and get your questions cleared till here. And I'll just set up show you an animation. Is it on?
We're reducing the volume.
Yeah. It's 0? अच्छा एक second. The compression is progressive and the actual particle vibrates at its So when the tuning fork is not vibrating, all the air molecules are equidistant, evenly placed. Now see what happens when they are set in vibration. What is density? Mass upon volume. The volume is reduced. Okay, 3 molecules spread out, the density will be less. Now the volume is reduced. Same number of molecules in less volume, so the density is more. And more they are closer, the pressure will be high.
So can you switch off both of them? It's very good.
Now when it is going back, it will spread out and compression will spread back. Okay, that's it. So I hope it is clear now how the propagation of sound takes place in the medium. So anybody has any question about what we have discussed so far? So we'll go ahead. सबने लिख लिया?
Yes, sir.
इस सबके नोटबुक में लिखा होना चाहिए सब, ठीक है? At least once you write it. Everybody is written? Chalo. So let's go further. Let's understand what are the different types of waves. So types of waves. So there are two types of waves that you are familiar with. One is sound wave and the other is light wave. These two waves you know, right? Radiation, light radiation. है ना? So sound wave falls under the category of mechanical waves. Mechanical waves. And this is called electromagnetic wave. Wave. So what is the example? Light. Okay. Mechanical waves have further two classifications: longitudinal and transverse. Transverse wave. Now this we need to understand. The example of longitudinal wave is sound wave. Okay. Example of transverse wave is water waves on free surface. Water waves on free surface of water. Also waves in stringed musical instruments. Stringed musical instruments. Okay? So two types of waves.
What exactly is waves in string?
That's what I'm asking you. So sound wave, how it travels? It is the air molecules are vibrating like this, and the disturbance is propagating, let's say, the listener is at the wall, you are the listener. So the disturbance is reaching you. But these molecules are vibrating parallel to the motion of wave, right? So basically, how to understand what's the difference? So in this case, the particles of the medium vibrate parallel to the wave motion direction. This is the velocity of wave, and this is the oscillation. So parallel oscillations. Okay? In longitudinal wave, the particles of the medium oscillate parallel. Whereas in this case, the particles oscillate perpendicular to the direction of motion of wave. So how you have you seen water wave? Like this. Or if you have a rope, okay, you give a jerk to a rope, you see a snake kind of motion. So rope is just going up and down at its position. What is traveling like a snake is the disturbance. Rope, because you are holding the rope, so the rope is not moving. What is moving is only disturbance. ऐसे करके वो आगे चलता हुआ दिखाई देगा. ठीक है? So rope is going up and down. The molecules, imagine rope is made up of billions of molecules. So those molecules are actually in slow motion. They are doing like this. So this molecule when it goes up, next molecule को ऊपर खींचता है, वो अपने next को खींचता है, ऐसे आता है, तो जब नीचे आता है, वो नीचे खींचता है, ऐसे, तब तक disturbance आगे चली जाती है. ठीक है? So that's what it is. Think of a water. So let's say you have a still tub of water. You drop some stone into it, and what you will see? First, you will see the ripples are created at the center. Then the ripples will spread. It will go towards the edge. Have you seen it? Throw a stone in a lake, you'll see the ripples are spreading out. Water is not moving. Water molecules are oscillating at its mean position. Only the disturbance, they are disturbing the adjacent water molecule. So all molecules are going up and down at different times. Understood? So now we'll represent this in the form of a graph. Is this clear?
Yes.
So here this is parallel oscillation with respect to wave motion. Wave motion मतलब disturbance motion. Okay. And here perpendicular oscillations. Who is oscillating? Of the particles of the medium. With respect to the wave motion. Okay. So this is called transverse. Why transverse? Because wave is traveling like this, whereas molecule is going across. That's why transverse. Two parallel line transverse. Have you seen that?
Yeah,
So transverse means something that is across. That's why the name transverse. Then what is light wave? Acha, mechanical wave, I did not tell you what is mechanical wave. Mechanical waves are waves that require medium to propagate. Electromagnetic waves don't require any medium to propagate. That's the basic difference. Okay? So both sound wave and these waves, they require material medium. So write down. Needs medium to propagate. What about light, electromagnetic? No medium required. Okay, that's how the sunlight comes to Earth. The majority of the distance traveled is space, empty space. Only the last 300-400 kilometers are Earth's atmosphere. So that is a medium. So light can travel also through a medium. But what kind of medium?
necessarily need a
Yes, but it's not a necessary thing. But what kind of medium? Can you see things across the wall? No, transparent medium. So it can travel through transparent medium and through empty space. Is it clear? So what is light wave? Light wave has transverse nature. Now here we said it doesn't require a medium. And transverse we defined that the particles of the medium go up and down as compared to the wave motion direction. But it can travel without a medium. So what is oscillating here then? Isn't it a valid question?
No.
When it can travel without a medium, disturbance was
Nothing oscillating.
because there is no medium, so there is no medium particle oscillating. But it has a transverse nature. There has to be some oscillation there. So the oscillation is electric and magnetic field. So let us say light is traveling in this direction. So it is surrounded by electric and magnetic field vector. Okay. So this is how it is. So E and B vector everywhere. So magnetic field is oscillating in this direction and electric field is oscillating in this direction and wave is propagating ahead. So there is 90 degree in the direction of motion. Okay? This oscillation makes 90 degree, E also. And it has 90 degree amongst themselves as well. Got it? So light wave has electric and magnetic field oscillating around it. Like two snakes. So how many planes are there? See, this is a horizontal plane, this is a vertical plane, and the edge is the direction of propagation. Got it? So it's like this: electric field vibration, magnetic field vibration, and it is now it's difficult to vibrate it like this. So two snakes. Imagine there is one snake traveling like this, one snake traveling like this. Together they are proceeding the same way. More advanced discussion in higher standards, not in this. Clear?
Yes.
Okay. Now let me represent it as a graph. So in this chapter, we are going to learn about only one type of wave, which is longitudinal wave. Only this wave. Okay, no other wave we are going to learn. Okay, we are only going to talk about sound wave, which is mechanical wave of longitudinal type. Clear? So now let us draw the graph. Graph of what? Displacement of the particle of the medium with respect to time. So this is how it will be drawn. Okay. So it could be pressure of the medium, density of the medium, or displacement. Pressure, density, or displacement, anything. So the pressure is maximum at this place where a compression is formed, right? And
something was there, crust and something.
crest and trough is what is compression here. We call it crest in transverse wave. Okay. So rarefaction for longitudinal wave is trough for transverse wave. Got it? Same wave can be used to describe both type of wave propagation. Here we get compression where the pressure is maximum and the density is maximum and the displacement of the particle is also maximum from its mean position, like this. When the compression will be formed, when the particle is gone maximum away from its mean position. That's when it will be nearest to the next particle. Got it? So this is where the compression is formed. So at that time, its displacement is maximum from the mean position. So this is the displacement plus A. We call it amplitude. What do we call it? Amplitude. It is the maximum displacement from the mean position of an oscillating object. Okay. So we can define some terms associated with wave motion. Or related to wave motion. So there are two things. Look here. When the particle is oscillating like this, so when it goes 1, 2, 3, 4, at that time disturbance has traveled one cycle. Got it? So there are two things happening here, three things happening here. When the particle is vibrating, let's consider for simplicity this way, transverse. Okay, when the particle is vibrating like this, so when it complete one oscillation, 1, 2, 3, 4, that time the disturbance started from here and it has traveled this distance. Got it? So this is what it is. So this is synchronous motion. So sometimes the first term is amplitude. So what is amplitude?
So increase in amplitude also increases the sound.
No, all particle amplitude is same.
Okay.
All particle of the air. So for this sound, for my sound, all the air molecules, okay, are displaced equally, and that is the amplitude. So it is the maximum displacement. Displacement of the oscillating particle from its mean position. During wave motion. Okay? During the passing of the disturbance or wave motion. So that displacement is called amplitude. So it is equal both on the positive side and negative side. ठीक है ना? Because mean position के आगे भी जाता है one extreme, फिर mean position पे आता है, फिर पीछे आता है. तो ये दोनों equal है magnitude में. Only the directions are opposite. That's why plus and minus. ठीक है? That is amplitude. So it is a distance or displacement. So its unit will be meter. Right? Its length. Next is time period. Next is time period. Capital T. What is time period? Time taken by the oscillating particle to complete one oscillation. Time taken by the oscillating particle to complete one oscillation. One oscillation or cycle. One oscillation. Or wave cycle. So wave cycle consists of one compression and one rarefaction. Okay, one compression and one rarefaction. Okay. Or one crest and one trough in case of transversal. So this is time period. Next is frequency. Okay. Next is frequency. Time period symbol is capital T. And the unit of time period will be, what is time period? Time. So unit of time is second. That's the unit. Unit of amplitude is meter. It is length. This is second. Now frequency.
So the number of oscillations in 1 second.
Yes, in unit time or 1 second. Correct. It is defined as the number of oscillations in a second. In 1 second. Correct? So for one oscillation, the time taken is capital T. Right? So in T second, one oscillation. Therefore, in 1 second, 1 by T oscillation. Correct? So that is frequency. So therefore, F is equal to 1 by T. T second में 1 oscillation. So 1 second में 1 by T. So 1 by T oscillation therefore is frequency. So what is the unit? So unit will be 1 by second per second, or it is also called as hertz. Hz. Okay? In the honor of the scientist, hertz. So that is frequency. So these are the terms needed to define a wave. Right. Next is wavelength. Wavelength symbol is inverted Y. Okay? Y ulta लिख दिया हमने. Slant and this
That
way.
looks like an X with an incomplete.
Incomplete X or inverted Y, and it is pronounced as lambda.
Sir, for the mean position to the maximum displacement, right?
No, that is mean to maximum is amplitude. So what is this length? It is the distance traveled by the wave in one time period. Okay, so distance traveled by the wave, distance covered by wave in one time period. So which distance is lambda from here to this dot? One side. It is also between two consecutive crests. Okay, or between two consecutive rarefactions. These are all lambda. So it is also time period. Time taken between two consecutive crest formation is also time period. Is it clear? So there are so many ways the same quantity can be defined, because it is a repetitive thing happening throughout. Does my sound changes when it reaches you, or when the next word coming, do you hear differently, or are you able to identify who is the source, who is speaking, right? Yeah, so it's the same thing happening at multiple levels, right? Okay. So this is wavelength. So this is also a length. So what is the unit?
Meter.
Meter.
Yeah.
Next is wave velocity, and this is the last term, wave velocity. Wave velocity, or you can say wave speed also, because it is traveling in one direction. So what is the wave velocity? Distance traveled in unit time, or displacement per unit time. So we know that when the displacement is lambda, time taken is capital T, time period. Right? So this is distance covered by wave in unit time. Where are the boys? Sleeping. Okay. Distance covered by wave in unit time. So what it will be? So therefore V is equal to lambda by T, correct? Isn't it? Because we know when the wave travels the distance lambda, the time taken by it is capital T. So it has to be lambda by T. And what is 1 by T? Frequency. So therefore V is equal to F lambda. That's it for the day. So V is equal to F lambda. So any wave velocity is given by this formula. And it is nothing but implementation of V is equal to distance upon time. The same basic formula implemented for wave gives you this formula. ठीक है? So we have covered a lot of things today. So any questions still here?
No.
Sure?
Yes.
Note it down. These are
This
the.
chapter is easier than any other chapter we did so far.
Oh, your level has gone up.
It's not that. This chapter is very basic.
Yeah.
though.
We did this last year also.
Yeah, we're pretty familiar with the terms and stuff. It's just wave velocity is new, that's all.
Okay. Then I think there is an experiment. See? My God. Just ready. This is the last lecture today?
This is the only lecture today, now we have MEPS.
Wonderful. So this is a experimental verification.
Bell jar experiment.
Bell jar experiment.
We did it last year in the class.
Can you explain?
The one in which something an oscillator.
What is it about?
It's about sound can travel. Sound does not travel through vacuum.
Yes. So basically what happens is, suppose you have a bottle in the shape of a bell, right? So it has a bottom, etc. Now a bell is fitted, the electric bell, which is powered from this, and it is cork fitted. Okay, and it is transparent wall, so you can see if the bell hammer is hitting the gong, then you will hear the sound. Okay, so basically initially when you fitted the bell, there was air into it. And at the bottom you have a vacuum suction pump. There is a pipe connected to vacuum suction pump. So initially the pump is off. Initially, look at this girl, where is she? Initially the pump is off. That time when the bell is, like when the switch is pressed, the ringing of the bell is, you are able to hear. How? Dekho, when this is ringing, it disturbs the surrounding air. The disturbance passes to the wall of the jar. Wall vibrates. That vibrates the surrounding air. And let's say the listener is here. So then the disturbance traveled and disturbed the eardrum. So he's able to hear the sound, right? Now while the bell is ringing, the switch is kept on. Now the vacuum pump is switched on. So the air is sucked out. So slowly as the air reduces, the sound becomes feeble to the listener. Sound becomes feeble. And moment when the entire air is sucked out, when there is vacuum, you can see the bell is ringing. You can see it. But now you cannot hear because the disturbance is not able to pass to the wall. There is no air molecule to carry the disturbance. Understood? That's how it is the Bell jar experiment, which proves that
sound requires a medium to travel.
yes. So which proves it is a which type of wave? Mechanical wave of longitudinal type. Okay. So the next is sound waves are longitudinal. This is a slinky. Slinky, right? Have you played with? Yes, the same slinky. That's where you can hear, see the compression and rarefaction formation very visibly. So if you have a slinky, just spread it on the table. Okay, one end if you can fix on the wall or make your brother or sister hold it for you. And one side you just give a jerk forward and backward. Then you will see the compression travel. So that's the demonstration of longitude. Wait for the bell to ring. Sit down, calm down. Very edgy. Who is going to teach you MEPS? Raghunath sir. Which topic is going on?
Everyone are different.
Everyone is doing different topic? Like what topic are you doing?
Triangles.
Triangles. Similarity of triangles?
Congruence, similarity.
Congruence and similarity. So right now doing congruence.
Yes.
Okay. What about you? You will discover after going there.
Yes.
Okay, good. You're still in a position to discover. What about you? Heron's formula, which is
root under S into S minus A S minus B S minus C.
formula to find the area of scaling triangle.
Of
Right?
any triangle.
Scaling or any
triangle.
Any triangle you can do,
Yeah.
but mostly it is used for scaling.
So So equilateral triangle has a different formula.
No, it's same thing can
Look
be.
at the three
It's a general
one.
formula. Heron formula is a general formula. It can be applied to any triangle.
Okay.
And then specific triangles have specific triangle specific formulas also.
But
Like
sir,
half base into height.
sir, but if we know what is A in equilateral triangle, why will we go for Heron's formula?
That's what I'm saying. So Heron is a general formula, but you have to know the side length, right? ABC, you have to know that. And what about you, everybody?
Triangle.
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 Triangle is what bothers you, it seems.
No.
Huh? Not the right.
Very quadrilateral, so we can
Triangles and quadrilaterals. Okay, basically triangle is one topic that comes in every topic.
Yeah.
And quadrilaterals in circles, everywhere you
So
just
quadrilaterals is like if it is four-sided quadrilateral, it's made up of two triangles.
yeah, you need to find the midpoint theorem and then prove it by that of triangles.
So a parallelogram is a square or a rectangle.
We need triangles for all of that.
So what you thought? Why such beautiful buildings, architecture? How do you
Lines
Triangles.
implement symmetry?
You draw lines.
So every aesthetic thing has a very complex science behind it, which becomes very simple. Just like speaking a language that you know.
Yeah.
It's just that familiarity, okay? So it is all going to be very, very simple for you. So don't worry. You're just starting.
Who is waiting MFS for us?
I'm not.
Okay, so somebody at 15, just do the.
And then does that.
Who does that? After 15, not before. Okay, bye.
Thank you, sir.
Ready for two Aditi, yes, next. No. आवाज आ रही ना तो इस बात खत्म क्यों देखना कैसा आ रही है अच्छा ये डिस्प्लेसमेंट आने की चीजें आ गई और हो गया 15 हो गया जल्दी बताओ डर लगता है